Hello. Today we'll be testing a noise filter I picked up on Amazon. Here's the product. This is a noise filter intended for audio applications, and this particular type of filter is commonly referred to as a ground loop isolator. It's a filter designed to reduce noise caused by ground loops. Through a series of experiments, we'll see what this filter actually does and how effective it is. But first, a quick shout out to today's sponsor. If you're looking for low-cost PCBs, I highly recommend JLCPCB. When you think of PCBs, you probably picture one of these, a hard green board. But JLCPCB also makes flexible ones. For wearable devices and highly flexible designs, flexible PCBs have become almost essential. JLCPCB now offers them at much lower prices, hoping more people will give them a try. 500 by 100 boards start at $2. Really cheap. You can even reinforce flexible PCBs with a variety of materials like polyamide, FR4, stainless steel, 3M tape, and even EMI shielding films. You can get coupons for flexible PCBs from the links in the description, so go ahead and give JLCPCB a try. First, let's take a look at the internal structure of the ground loop isolator. At the beginning of the video, I described it as a noise filter, but its primary function is actually to isolate the signal electrically. Noise can be caused by ground loops. This transformer helps eliminate that noise by electrically isolating the signal path between the devices. That's the basic structure of an audio ground loop isolator. This part is the transformer. This is used to transform the voltage of the audio AC signal. I mentioned that it transforms voltage, but in many cases the transformer ratio is 1.1, so the signal level stays the same between input and output. Thanks to the transformer, the ground loop is broken at this point here. Next, let's look at how the ground loop isolator works. Before that, I'll remove the transformer from the diagram for a moment. I've temporarily replaced it with direct wiring. Let's say we have device A, which outputs a signal, and device B, which receives that signal. The two devices are connected by wiring. Both device A and device B are grounded. For simplicity, let's assume they are grounded at different points, which I'll refer to as ground A and ground B. Now, let's assume there is some unknown source of noise connected between ground A and ground B. In this case, a noise loop is formed along this path. As a result, the noise is transmitted to device B. Although simply having a ground loop does not necessarily mean that noise will always occur, under certain conditions it can sometimes cause problems like this. Now, let's conduct a simple experiment. This circuit does not include a transformer. To make the experiment easier to understand, I'm using a signal source as device A and a speaker as device B. The signal source and the speaker are connected by wires. I will generate a signal, which is a noise source between ground A and ground B. In this experiment, the load is a speaker located only a short distance from the signal source, but in real-world applications, the wiring can sometimes be several meters long. I've prepared a separate noise source. I'll connect it between these two grounds here. Now, let's listen to the ground loop noise in this setup. First, let's listen to the signal by itself. What you're hearing is a 440 Hz sine wave. Next, I'll inject a noise signal to the ground. Here we go. This time the noise frequency is set to 2 kHz. Can you hear it? Let me explain what is happening in this circuit. This loop here, which corresponds to this loop in the actual circuit, carries current when voltage is applied across it. Although it's not shown in the circuit diagram, the actual wiring has some resistance. When current flows through it, a voltage drop occurs, which changes the voltage applied to the speaker. As a result, you hear unwanted noise. However, if a ground loop isolator is placed here, the transformer of the ground loop isolator electrically isolates the connection, eliminating the loop through which current flows. Now, let's actually test how effective the ground loop isolator is. First, we'll output a 440 Hz sine wave from device A. Here's what it sounds like. Next, we'll inject the ground loop noise. Since the ground loop isolator is in place, we shouldn't be hearing any noise. Now, let's begin. We can still hear it. Why is that? We shouldn't be able to hear this 2 kHz noise signal, but we actually can. Something seems to be wrong with this ground loop isolator. I checked the product page and it says that it uses a transformer. If it really uses a transformer, these two terminals should be electrically isolated from each other. Let's measure the resistance between the terminals. This one and this one. They're not isolated from each other. Let's check the other terminals. They're also connected. Lastly, this one and this one. They're connected as well. Something feels off. Since something seems to be wrong, I'm going to take it apart. There we go. What is this? Can you see it? This is really bad. This isn't a ground loop isolator at all. The terminals are just wired directly together inside. This is terrible. Since it just connects the terminals together, it's basically nothing more than a simple pass-through adapter. It has no functionality as a ground loop isolator at all. This looks like a complete scam product. Even though I ended up buying a useless product like this and things didn't quite go as expected, but I still want to see how effective a real ground loop isolator actually is. So I built this circuit myself. I designed a circuit like this and had the PCB manufactured by JLCPCB. I bought the components, including the capacitors, resistors, and transformers, from AKIZUKI and DigiKey. All the parts are listed in the description, so feel free to check them out if you're interested. In addition to the ground loop isolator function, I also included a high-pass filter that cuts frequencies below a few dozen hertz. The main concern was choosing the capacitor. I decided to go with this PML cap from Rubicon. It's a type of film capacitor that's both compact and capable of high capacitance. Its capacitance also changes very little, even when the applied voltage varies. Just from the specs, it already sounds impressive. Someone at Rubicon told me that it's actually often used in audio applications. So, let's start assembling the circuit. Here's the finished circuit. The left side is the input, and the right side is the output. The input and output grounds are separated. There are two signal channels, and each channel has its own transformer. I used a Sansui transformer that I bought from AKIZUKI. Now, let's see how much of a difference a ground loop isolator makes in terms of noise. First, without the ground loop isolator. I'll input the signal first and then inject ground loop noise. You can hear the noise. Next, let's try it with the ground loop isolator. First, I'll input the signal. As you can hear, the volume is slightly lower due to the effect of the ground loop isolator. Next, I'll inject the ground loop noise. Even after injecting the noise, I still can't hear any ground loop noise to my ears. Next, let's take a look at the waveform to see how much effect the isolator has. We're looking at the waveform without an isolator. The circuit has been modified to make the effect on the waveform easier to observe. What you're seeing here is the signal waveform at the output section. At the moment, no ground loop noise is being injected. Now, I'll inject 50 Hz ground loop noise. As a result, the waveform appears to have a 50 Hz signal superimposed on the original signal waveform. This means that the ground loop noise directly appears in the output signal. Next, let's look at the case with a ground loop isolator. We'll inject ground loop noise. So, what happens? There is almost no effect at all. The waveform remains unchanged. This is the power of the ground loop isolator. However, the isolator cannot eliminate every type of noise. Let's see what happens when high-frequency ground loop noise is introduced. I injected ground loop noise at around 40 kHz. As you can see, a high-frequency signal is superimposed on the original signal waveform. This noise is leaking through the parasitic capacitance between the transformer windings. Now, let's check how much ground loop noise the isolator can actually remove. In this setup, we're injecting ground loop noise between the grounds. Channel 1 shows the amplitude of the ground loop noise, while channel 2 shows the output amplitude, so we can see how much noise is being removed. Basically, we're comparing the frequency characteristics of channel 1 and channel 2. Let's wait for a while. At lower frequencies, it's around 100 dB, so the ground loop noise is being eliminated quite well. This indicates a high common mode rejection ratio. But as the frequency increases, beginning at around 100 Hz, ground loop noise starts to appear at the output. As I mentioned earlier, this is the signal passing through the capacitance between the transformer windings. That's what's causing the noise. As the frequency increases, ground loop noise leaking through to the output side of the transformer gradually begins to appear. At 100 kHz, it's about minus 43 dB, so if there is 1 volt of ground loop noise, about 0.01 volt will be superimposed on the output signal. That's about the level. The characteristics can vary quite a bit depending on the transformer used. While we're at it, let's also take a look at the frequency characteristics of the ground loop isolator I built. Earlier, we measured how much ground loop noise could be removed. Now, we're measuring how well the audio signal is transmitted without degradation. Let's leave it for a while until the measurement is complete. The measurement is complete. These are the results we obtained. The frequency characteristics are pretty much what we expected. Since we've added a high-pass filter, the low-frequency components are attenuated. Looking at the cutoff frequency, it's around 120 Hz, which feels a bit too high. It may be better to lower the cutoff frequency somewhat. After that, the characteristics remain flat for a while. In this region, the phase is starting to lag a little. This is due to the characteristics of the transformer. At the same time, the gain also starts to drop slightly. The high-frequency cutoff frequency is 47 kHz. It seems there shouldn't be any issues when used for audio applications. Beyond that point, the gain gradually starts to roll off. At 100 kHz, it's about 6 dB. I think the result is fairly good. Therefore, the ground loop isolator I built should work well for audio signals within the approximate range of 120 Hz to 47 kHz. For the high-pass filter, you can just adjust the cutoff frequency to whatever you prefer. I put it in this aluminum case in case I ever need it in the future. It's connected like this inside. The XLR connector was reused from the scam product. Looking at it like this, it actually looks pretty nice. So today we explored the structure and role of the ground loop isolator, and also tested how effective it actually is. Ending up with a fake loop isolator from Amazon caused some trouble, but I was able to build my own and test it in the end. In terms of effectiveness, it can suppress noise to the point where it becomes inaudible. However, only at low frequencies up to a few hundred hertz. As the frequency increases, some noise begins to leak through the capacitance between the transformer windings. Since I've never encountered ground loop noise in practice, I don't really know how effective this will be in an actual environment. Still, I might end up needing it someday, so I'll keep it stored away. Thank you for watching. See you next time.